In the previous example, we solved for the transfer function of an ideal translational mechanical system. We have another example wherein we will have to consider the friction due to the references, not the friction as in the basic element. So this one, if you can see here, we have a wall. So this wall will cause a friction to our system. So if we take a look at this example, we have the spring with one end connected to the reference, and it is connected to a mass M1. So in between M1 and M2, we have B1 dash pot 1, and then we have K2 spring 2 in parallel. And then the external force or the applied force is connected or applied directly to the mass 1. So it creates a displacement x1 to m1, and the output is x2, which is the displacement in the mass 2. So the difference with the previous example is that we didn't have this reference wall here. So the friction that we're talking about is this friction in between the mass and the wall. So we don't have a friction involved in M1 because we put these wheels here, which means that we will neglect the friction in between them. Okay, so here we have 1, 2, 3, 4, 5 translational mechanical system elements. So again, what we need to do to solve for the transfer function of a mechanical system is first, we have to identify if it is either translational or rotational. So for this one, since we have M1 and M2, and we have a force instead of a torque, and we have displacement instead of angular displacement, we can then conclude that this is a translational mechanical system. So step 2, we will have to draw the free body diagram. So again, the number of free body diagrams required would depend on the number of masses. So we have M1 and M2, therefore we have 2 free body diagrams. So first, for this one, for M1, let's check on all the forces connected or applied to it. So for M1, we have F of T, which is the external force. We have F of K1. So again, the direction of the force will be different from the applied force because this FM, FK, FB are the opposing forces. And then we also have FB1. And lastly, don't forget the opposing force due to the mass itself. So for that, remember that there's no indication, there's no connection because the force is in the mass itself. So FM1. And then lastly, we have FK2. So it doesn't matter if it's if the arrow is drawn here on the left side, right side, or bottom part of the box, as long as the arrow is pointing towards or from the mass. Okay, so we have 1, 2, 3, 4, 5 forces. And then don't forget as well to write the displacement. Then free body diagram number 2 is for M2. So the forces connected are FM2 itself, FM2, FB1 for this dash pot, FB2 is actually from the friction between the surface and the mass. So we didn't indicate negligence for friction there, so we have to consider this B2. In some examples, I might not actually be giving this one, but you have to assume that there is friction in between those two surfaces. So we have to indicate FB2 as well. And then lastly, don't forget this FK2. So again, for the output, we have displacement 2, X2. Then we already have the free body diagram. We'll now move on to getting the force equations. So one force equation is equivalent to one free body diagram. Therefore, we will have two force equations. So for mass 1, we will have to get the equivalent forces of each of these forces. So Fm1 is equal to m1d squared x1 over dt squared. And then Fb1, for Fb1, you will notice that both ends are free, so it is not connected to a reference. Therefore, we will have to use the formula for case 2. Also, so as you will not be confused, sometimes if this is the case, you can already indicate here, like put some note here that this is for x1 minus x2, and same with this one, fk2. So that's for when you are writing the equation, you will not forget to use the correct formula. So it will be the same for case of m1 as well, I mean m2. So just write x1 minus x2 here. This is not required, but this will be helpful in solving for the equations. So fb1 is equal to b1 derivative of x1 minus x2 over dt. For fk, it's only k1 x1, and then for fk2, this one, we have x2 times, k2 times x1 minus x2. So to get the equation, we will have to equate f of t is equal to the summation of all the opposing forces. So we will just have to substitute fm1, fb1, fk1, and fk2. So we will come up with this equation. And then next step is to take the Laplace transform on both sides. So again, we use Laplace transform because in getting the transfer function, we cannot use the ODE. We have to convert it to the S domain. So f1 of t magiging f1s is equal to m1. So if you will notice, m, b, and k, we don't actually do anything to them during Laplace transform because we don't consider them as variables. So they are mere coefficients. So we will not do anything with this m1. So just copy that, and then we'll actually use or apply Laplace transform with this term d squared x1 over dt squared. So for second order, we will have second order s as well. So s2 or s squared times x1 of s plus b1s s x1 of s minus x2 of s. So everything will be in s domain. So just apply Laplace transform on all the terms and you will come up with this. And the next step, once you already have everything in S domain, you have to factor out the displacements, which are x1 of S and x2 of S. So just combine the like terms and factor out these displacements. Then this is your Laplace transform equation number 1. Then for mass number 2, so ito yon yung mass number 2. I'll just copy para mas madali yung reference. Okay. So this is free body diagram number 2. So the forces involved are Fm2, that's m2 d squared x2 over dt squared. Fb1 is equal to b1 d x2 minus x1 over dt. Yung Fb2 is simply b2 dx2 over dt. And then lastly, Fk2. So since we don't have here any applied force, we will just have to equate the equation to 0. So 0 is equal to the summation of all the opposing forces, and then substitute those opposing forces. So m2 d squared x2 over dt squared plus b1 d x2 minus x1 over dt, and then b2 dx2 over dt plus k2 x2 minus x1. So this is actually your equation number 2. But this is still in time domain as ODE. So we have to take the Laplace transform on both sides. So Laplace transform of 0 is also 0. And then m2, just copy. D squared will be s squared. And then just apply Laplace transform on all these terms, and you will come up with this equation. So again, you will have to factor out the displacements x2 of s and x1 of s. So first, you have to combine the like terms. So lahat ng x2 of s pagsamasamahin natin, and same with x1 of s. So for this one, what you want to do is to separate x1 of s and x2 of s in the different or in both directions of the equation. So yung isa is nasa kabilang side. So I chose x1 of s so that I can use this equation number 2 to substitute to Laplace equation number 1. Because what we're trying to do is we're getting the transfer function, and by definition again, transfer function is equal to Laplace transform of output over Laplace transform of input. So our output is x2, and the Laplace transform of that is x2 of s, and our input is f of t, and the Laplace transform of that is f of s. So we want to eliminate x1 of s in our equations. That's why we have to equate the equation to x1 of s. So now that we have x1 of s from equation number 2, we can substitute this to equation number 1. So our equation number 1 is this. So substitute x1 of s from equation 2 to equation 1, we will come up with this transfer function, b1s plus k2 over m2 s squared plus b1s plus b2s plus k2 times m1s squared plus b1s plus k1 plus k2 minus b1 of s plus k2 squared. So it is not a strict process to follow substitution, but you can also use elimination method to simplify your equation.